Segment 3. What methods are available for decontaminating oil?
We had said before that we would examine the various methods that are in use in the industry today for removing water and perhaps attempting to remove other contaminants from lube oils. The first one we should look at is called the coalescer. The coalescer uses special cartridges to combine small dispersed water droplets into larger ones. And coalescers are in use literally at thousands of airports. They remove water from jet fuel so that when a plane goes into the high altitude regions, into cold conditions, the water does not freeze up in the fuel lines. These coalescers, utilizing cartridges, are affected by the properties of the hydrocarbons, specifically the interfacial tension, which tries to keep the hydrocarbon particle and the air particle, if you want to call it that, together. They are efficient and effective for a relatively narrow range of lube oil viscosities. However, it's true that they are very cost effective. We, for our part, must realize they remove only free water. This is what a coalescer looks like. It would have a cartridge inside of it, which we might call a coalescer cartridge. A second set of cartridges is called separator cartridges. And you can see here how the contaminated lube oil enters at the inlet, lower left-hand corner, and the clean oil comes out at the outlet connection on the lower right-hand corner. The drain connection is intended to remove the free water that has been collected. Centrifuge methods are prevalent very frequently in the industry. Centrifuges remove all except trace amounts of free water. 20 weight parts per million is normally still left in the oil as free water. They are suitable for a relatively narrow range of specific gravity. They will not remove entrained gases. They are good for the purpose of removing very large slugs of water, and this is their primary function. We see one of the typical centrifuges in this picture here. There's an overflow port for the purified oil. There's an overflow port also for the water, and it's clear that the center rotor is rotating at high speed. Vacuum dehydrators have the principal attribute of being most versatile. They remove both free and dissolved water. They cover a wide range of viscosity and specific gravities and can be used to restore transformer oils. Also, of course, they will remove the light hydrocarbons, which, as we said earlier, are frequently contaminating seal oils in process gas machines. Here would be a good picture of a mobile unit. This unit is used in a large plant on 36 reservoirs. It is wheeled from location to location for the purpose of removing water and other constituents that have contaminated the lube oil. Vacuum dehydration, in summary, is the preferred method because it not only removes water but also restores the flash point, removes light hydrocarbons and H2S, degasifies the oil. And as we said a minute ago, the principle is based on the simultaneous application of heat and vacuum. In conclusion then, as we examine these various methods, we can make the statement that centrifuges and or perhaps coalescers, if they are used, must be operated continuously. They are suitable for installations with close viscosity control. They require careful engineering. They are not suitable for installations where you try to remove dissolved water or where you're trying to remove gases that have been entrained in the oil. Vacuum dehydrators allow the intermittent operation of the purifier simply because they are the only piece of machinery or the only equipment that gets you down into the dissolved region of water. They are suitable for installations with varying degrees of light hydrocarbon contamination. And of course, they too require careful engineering. Let's examine this schematic of a modern vacuum dehydrator. The lube oil, which comes from the bottom of a reservoir, enters at this point here, goes through oil-to-oil exchanger because, remember, the purified lube oil here is at an elevated temperature, higher temperature than the incoming oil. Consequently, if economics suggest that we do this, we have the option of putting an oil-to-oil exchanger here to economize somewhat. We go with the oil into the vacuum dehydrator through this particular pump. Here we might have a sample drain valve. We go through a filter for filtration of particulate matter. After the filter, we send the contaminated lube oil to the top of this vacuum and heat vessel. We indicate here some heating system which surrounds the vessel. The lube oil, which is contaminated with water and perhaps some gas constituents, is now flowing on these baffled or slanted trays. Since this entire region exists at a vacuum and at elevated temperature, the liquid water will now flash off, and it can be pulled off by virtue of the vacuum pump, which we see over here. Before we arrive at the vacuum pump, the vapors go through a condenser system. And in this condenser system, we are primarily interested in condensing water vapors so that these water vapors can be discharged through a drain as shown right here. We did indicate that the clean lube oil goes to the bottom of this vessel. From there, through an automatic flow control valve, back to the oil outlet pipe or oil outlet hose, and from there it returns to the lube oil reservoir that we're planning to purify. The only other thing to be mentioned is that the non-condensables will go through the vacuum pump, and we now have the option, after they leave the vacuum pump, to put them into a flare system, a collecting system perhaps made of charcoal filter material, or in some cases we may opt to send these non-condensables directly back to the atmosphere. And that pretty much completes a review of a typical schematic.